What you are looking at right now is something that's known as R3, or space, or 3 space. It's how we graph things in 3 dimensions. So up until now, we've been doing everything in R2. That's just the Cartesian plane that we're used to. It's basically saying that you're measuring all the real numbers in 2 different directions, so along the x-axis and along the y-axis. But what we're looking at here is actually extending everything into R3, which is, again, 3 space. So it has an x, a y, and a z axis associated with it, so that now we're actually looking at things drawn in 3 different directions. A point drawn in 3D, therefore, has to have not 2 coordinates, but 3 coordinates. So a point A is going to have an x, a y, and a z coordinate associated with it. Now that Cartesian plane that represents R2, that's one of infinitely many planes that exist in 3 space. Now, as far as key planes of interest, there are really 3 that we're going to talk about. The first is the xy plane. That's a place where points only have x and y values. And in this plane, points can be written then as x, y, 0. Because they don't have a z coordinate, we would just represent it as being a value 0. The second key plane of interest is the yz plane. In this plane, points only have y and z values. And when points are written, they're written with coordinates 0, and then the y value, and then the z value. The third plane of interest is the xz plane. Points in this plane will only have x and z values, and so a point might be written out x, 0, z, where x and z represent the numerical coordinates for that point. So that's a crash course into how geometry works in general when we're working in 3D, but now to connect that all to vectors. We say that if A is a vector in R3, then A can be written as a column vector with components A1, A2, and A3. These components correspond to the X component, the Y component, and the Z component. As far as how we would describe that graphically, your X components still mean left or right movement. Your Y components still mean up or down movement. But the Z component becomes a little bit trickier. We would actually say that that represents going into or out of the surface that we're drawing on in 2 dimensions. So is it going into the page or is it coming out of the page? And that's how we would represent 3 dimensions. Now, of course, working in 3 dimensions brings with it different basis unit vectors that we use to define how vectors are made. So our basis vectors in 3 dimensions are denoted as I, j, and k. I is still the basis unit vector in the direction of the positive x-axis. J is still our basis unit vector in the direction of the positive y-axis. But we introduce now k to be our basis unit vector in the direction of the positive z-axis. As a result, that vector a from earlier can be written using the basis unit vectors as shown here, with a1 being multiplied with I, a2 by j, and a3 by k. So we're really just extending the definition of that vector by an extra term. So what does that mean for how we calculate magnitude of a vector in 3 dimensions? Where our vector was made up of components that could be formed into one right-angled triangle when we were in 2 dimensions, what actually happens in 3 dimensions is we end up just making multiple right-angled triangles. And so Pythagorean theorem and the whole justification we used for magnitude in the past still extends to 3D. So what we end up with as our equation for the magnitude of a 3-dimensional vector is actually very close to the 2-dimensional equation. We just take each of the components squared, sum them, and square root the result to get the magnitude of those vectors. And how do we find the vector between 2 points? Well, that's no problem either, because the definition for that also extends to 3D. If I have a point A and another point B, both in 3 dimensions, then my definition for finding the vector between 2 points extends into 3D by just adding in a third component that comes from subtracting those coordinates of the point right up to the z coordinate. So all the rules we've established for vectors in 2 dimensions extend into 3 dimensions as well.